This video is going to prove the Pythagorean theorem using similarity. So here we have a right triangle with the right angle at angle A. And the first thing I'm going to do is draw an altitude. So an altitude goes from one of the vertices to the opposite side, intersecting it at a 90-degree angle. So these two angles right here are 90 degrees. This is the height of the triangle if I were to have this be the base. I'm going to label this point right here D. We know that we can prove triangles congruent using angle-angle similarity. So all we need for that is to have two angles in common and two angles congruent, and then our triangles are similar. So if we take a look at this small triangle up here, is that similar to this big triangle in black? And I'm going to say that it is, because they both have a right angle. This, in the big triangle, it's at angle A. In the smaller triangle, it's at angle D. And they also both share the angle at B. So by the reflexive property, they share an angle, so that's congruent, and they both have a right angle. Angle-angle similarity. What about this second triangle, the sort of medium-sized triangle, and the big one? And if it's congruent, if the medium size is congruent to the big one, similar, then it's also similar to the small one. So let's check this one out. We know that they both have a right angle, and they also both share angle C. So again, by the reflexive property. And because they both share that angle, it's congruent. They both have a right angle. Those angles are congruent. So by angle-angle similarity, we have three similar triangles in this picture. We're going to need to use that in order to prove the Pythagorean theorem. So I've just redrawn that image here so that we can have it to look at as we continue. I've also redrawn our three triangles. This being the large one, ABC. This one being this medium-sized one with the right angle at D, shortest length going to A, and then the other leg, the hypotenuse, as AC. And this is our smallest one, the one right here, with the right angle at D, DB being the shortest side, and BA being the hypotenuse. So I wanted to, and I flipped them around, you'll see, because I wanted it to be very clear. So again, these are our three right angles. And all of these triangles are similar, as we showed in the last slide. So because they're similar, I can set up proportions about their sides. So in similar figures, the sides are proportional. So the ones I've chosen were strategic in proving the Pythagorean theorem, but any proportion that I set up among these sides would be true. So here I've done AB, so I got AB, this side here, over BC, over the hypotenuse, and that proportion needs to be equal to BD, if I look to my smallest triangle, over BA. So, smallest side over hypotenuse of my biggest triangle is equal to smallest side over hypotenuse of my smallest triangle. We know that those ratios need to be equal. I can then cross multiply. So once I cross multiply, let me get a different color here, I'm going to get BA times AB, which BA is the same as AB, so I can write AB times AB. And if I cross multiply this way, I'm going to get BC times BD. I set up another proportion, where here I have AC over BC, so this is in my bigger triangle again, AC, my second leg, my middle side of my triangle, AC over BC over the hypotenuse is going to be equal to DC over AC. So here we know that these proportions, these ratios, must be equal. We have the middle leg over the hypotenuse of my large triangle is equal to the middle leg over the hypotenuse of my medium triangle. And again, once I cross multiply, I got AC times AC, and that's going to be equal to BC times DC. So using similar figures, I've set up these proportions, and they must be equal. If we put numbers in here, this ratio would have to be equal to this one. That's what makes them similar, those proportions. Now, these two equations are important in trying to prove the Pythagorean theorem. So what am I going to do with them? I'm actually going to add those two equations. So we'll flash back to algebra here. I'm adding these two equations, and I just rewrote these from the slide before so that we can continue to work with them. So AB times AB plus AC times AC. So AB times AB, we know that that is AB squared. AB squared. And when we add it to AC times AC, that's going to be AC squared. So this part so far reflects adding AB times AB plus AC times AC. We've dealt with the left side of our equal sign. Now let's add to the right. We're going to have BD times BC plus BC times DC. And we couldn't put them into cute little formulas like that because we didn't have the same thing being multiplied by itself. But as you might notice, we do have a BC in both of these terms. So what I can do, if let's say both these things are being multiplied by 2, I could pull the 2 out and then add the others. So I'm going to pull a BC out of this equation. And what would be left when I pull that out is going to be BD plus, this plus continues, plus DC. And that is still equal to AB squared plus AC squared. Next, I can see, looking back at our original figure here, what is BD plus DC? And you'll notice here that BD is this length here, DC is this length here, and by the segment addition postulate, BD plus DC, this is going to be equal to BC. So now I can replace BD plus DC as BC. So now I have BC times BC. And that's extremely helpful because now I have, let's go back to red so it really pops here. So now I have BC squared. BC squared. And BC squared, again, is going to be equal to AB squared plus AC squared. Now, let's take a look. I've erased the, I should leave the right angle, but I've erased the altitude so that it's very clear that now we're just looking at a right triangle with the same letters in the same place as our original figure. And what this is saying is AB, this length here, AB squared plus AC squared is equal to BC squared. One leg times itself, one leg squared plus the other leg squared is equal to BC squared. So we usually see this as A, B, C for the sides. AB would then, but AB is then now called A squared plus AC is now called B, and the squared stays, and that's going to be equal to BC, which we've now labeled C squared. So this is how you prove the Pythagorean theorem using similar triangles.